Hello, welcome to another problem session. So today we have the next topic in the waves. We have done two interference where 2 point sources were created, and now we're going to do diffraction. Now the diffraction is very strange actually. It looks like you have just a single slit. So when you have a single slit, you don't have a second wave to match to get interference pattern like this, right? A pattern of bright, dark, bright, etc. So it's very surprising that when you have a single slit, you can get pattern if the conditions are right. So what are those conditions? Well, number one is this is a again has to be coherent source. So say we have a single wavelength here. So that's and we create a source. So here is a source, ultimate source, and it's far away. So what is called Fraunhofer diffraction. So this is also far away. So when it hits here, we're going to do almost planar. If it's not almost planar, then some of the formulas that we're going to do is not really applicable. But here we're going to say you have a slit, and then there is a screen here, and this width of the slit, this width is D, and D is going to be much less than L. So the formula here looks like the double slit interference, but not quite. So when this is the case, then we can show that the direction, the minima, is easy to show. Directions to minima, meaning the dark places, okay? We can show like theta 1, so D times sine theta 1 equals actually just lambda. So this is the minima. This is kind of like a opposite of the formula wise, okay? So if I have any of these theta, so theta ith theta, so let's ith theta or nth theta, I'm just going to use m. M theta is m lambda, and m can be of course m is 0, then straight, of course, is wrong, right? So m is 1 plus or minus 1 plus or minus 2 plus or minus 3, etc. Between the two dark directions, there will be a bright fringe. Okay, so this will be the bright thing between this dark direction and this dark direction. So let's use this formula first, and then find out why this is true. Okay, that will be at the end of the video. So to answer this problem, suppose I've kind of memorized this formula somehow, and I want to answer this problem. So part A will simply be find the locations of 4 minima, if possible. It should be, if possible, because you can see that this will fail. So say D sine theta 1 equals to lambda, right? But this cannot be, this has to be less than 1, right? So it So first one, like d sine theta 1 equals to lambda. So, but sine theta 1 has to be, if I look at the absolute value, has to be less than 1, which means lambda over d has to be less than 1. So if the slit is very narrow, so if the lambda is 0.55 micrometer, and if d is equal to 0.5 micrometer, then you won't even no dark spots, places, meaning no minimum. So on the screen, in that case, on the screen, you're going to get just all of this will be, the entire screen will be lighted. Of course, it will vary the intensity. It will be more intense here, but less and less over here. So it's kind of like that. So the screen will be entirely lit if this is the case. But here we don't have that case. We have d equals to over here. So if I look at with an m, let's look at the m. So theta m, and so in this case m lambda has to be less than 1. So there will be some m, m is 1, 2, 3, 4, like some m, so for which this will get violated. So violated for m greater than m equals to d over lambda. So this is the max m value allowed, max m value allowed. It's very important to, whenever you're using in a formula some sine theta or something like that, you must make sure that the formula makes sense up to a point, and when the formula will get violated. Okay, so let's just work it out here. So sine theta 1 is lambda over d, and lambda is 0.55 micrometer, and the d is 2 micrometer. So we can just get a theta 1 from this. Theta 1 will be just use a calculator. I will use this. In the Python, I get maybe 180. Okay, so say convert equals to 180 slot math.pi, so that angle conversion, and then we will have theta 1 is equal to, convert this, and a sine, I think it's a sine or arc sine, maybe arc sine, I don't remember this, 0.55 divided by 2, so it's maybe a sine, I think it's math. Okay, so T1 is 15.96 degrees. So this is 15.96 degrees, which we can just round it to 16 degrees. So that's the answer for A1. So we'll get theta 1 equals to minus theta minus 1. That's exactly symmetric. 16 degrees. You got 2 of them and you want to know 4 of them. So let's do sine theta 2 will be 2 lambda over d, and so it's going to be 2 times 0.55 micrometer over 2 micrometer, and so theta 2 will turn out to be equal to minus theta minus 2, and that's going to be arc sine inverse 2 times 0.55 over 2, so this is 0.55. So let's look up again so T2 convert math a sine 0.55 and T2 will be 33.4 degrees. So this is 33.4 degrees, not quite double of that, it's more than double. How about theta 3? We already got the answer, this 4, okay? This 4 angle is good enough to tell 4 minima on the screen, okay? So that's already answered, but let's do the theta 3 just for the heck of it. So arc sine inverse 3 times 0.55 over 2, and that's going to be so T3 is going to be 2 times this, 3 times that, 3 lambda over D2. So, and that's 55.6 degrees. 55.6 degrees, with same thing is minus theta of minus 3. How about theta 4? Theta 4 is equal to arc sine inverse 4 times 0.55 over 2, and you are going to run into trouble pretty soon. So let's see, we run into trouble. T4 is 4 times as much. So sure enough, we run into trouble because numerator 4 star 0.55, that's 2.2. So this is definitely not gonna work, right? So this is trouble. Let's use a red thing, trouble. So that means m equals to plus or minus 4, not allowed by this formula. So this is the maximum that we're gonna get in this case. Okay. All right. Let's answer how wide is the central maximum. Okay. So when we want to do B, we have this is the central maximum. So this is the one we're looking at. So this one was theta 1 and this one was theta minus 1, and so we want to know how wide it is in terms of, say, delta y. So this is what I want. Okay, so how would I get this distance is L, and you can already see, you can find out this distance. Let's see, delta. So delta y is 2 times delta because symmetry, and so you can see the delta will simply be this divided by L is tangent L times tangent theta 1. Now L is really not given in this problem, so we won't be able to solve this problem for delta y. Let's give you the L. L is equal to maybe 1.5 meter. Okay, so 1.5 meter, and tangent we had a 16 degrees, right? So we will do this calculation again, and I think we should do T1. Let's see, T1 we already have, but we need to convert back T1 by, so that's the radian. So we will have tangent 1.5 start math tangent of T1 by, so we need to argument inside these functions are given in radians. That's why I'm converting back to radian, and so this will be 0.4. Okay, so this will be 0.43. So delta y will be 43 meters of 43 centimeters, so 0.86 meter, which is 86 centimeter. Now this is quite wide, so this thing here is very wide here. Okay, it just it becomes this wide because of the the d we had, and L we had, and lambda we have. Okay. Now, so this solves the problem. We could have asked what is this angular width. So this angular width, which is often written like this, for W for width, this will be 2 times this theta 1, and so this just 2 times 16 degrees, which is 32 degrees. So this is another way to ask the same question. Okay, now problem is solved now, but it begs the question is, where does this formula come from? This formula itself for the minimum direction for the minimum. We don't have 2 sources of waves. There's only one wave here. So how come we got the interference like formula where we needed the 2 waves? Okay, so we're gonna address that in the next 5 minutes or so, over the next 5 minutes. Okay, so, all right. Okay, so now we want to address where this formula came from. Basically, you can think of it in terms of Heisenberg's principle. In what Heisenberg's principle is, we have. So let's look at this. When we look at the slit, there is a cross section we look at. Or maybe I want to just get a little bit wider slit. Just yeah. So let's look at a wider slit. So we have a just at the slit. We had a wave. We have a wave which looks like that. Now this wave, of course, the slit is coming out like that. So this is a wavefront in 3 dimensions looks like that. And each point of this vibrates independently. That's Heisenberg's principle. Each point vibrates independently and creates new waves. So if you look at just the point on the slit, in this cross-section point, this white line, say this is the y-axis or something like that. So each point is creating its own wave. and these are the waves, and so this is a primary wave, and then those waves, those wavefronts create their own waves, secondary waves. So this is the Heisenberg principle, that waves, the wavefronts, each point of the wavefront, the way it moves in space is it vibrates and creates new secondary waves, which where now wave from here and here will make a new wave, and that new wave front will the points the new wave front will make secondary waves, and that's the waves travel. So in that way, each of these point on this wavefront is actually a source of wave. So it's not a single wave, it's like infinitely many waves. And to do a math for this, you will have to do continuous integrals and things like that to derive this formula. To derive this formula, by adding waves and applying the superposition principle for the wave, you'll have to do a pretty decent amount of math, okay? And we're not going to do that. So there is actually a nice trick. So we just look at this front. So this is the front. And I want to know on the screen, so let's see, here is the screen. As the screen is here, where is the minimum? First minimum above that horizontal line. Well, one way there will be destructive interference here. A minimum means like no light there, so this was a light. That point originating here and a wave originating the very first over there, they kill each other. They're out of phase. So this wave and this wave out of phase. These two will be out of phase. What do we mean by out of phase? Meaning delta R is lambda over 2. So if this wave comes in at the, like over here, this wave comes in over here. So wherever, if it comes at the peak, the other one comes at the trough at this point. That will be the difference, the distance will be lambda over 2. Okay, so now we effectively, what we have done is, if you look at, if this angle direction is theta, so this is the theta. If you remember the formula, and this is actually d over 2 now. D over 2 now. So this is d over 2 sine theta. Let's call this theta 1, the very first one I'm looking at. Theta 1 equals lambda over 2. And so d sine theta 1 equals to lambda. And that's m equals to 1. M equals to minus 1 will be exactly like over here. So it's going to work out exactly that way, right? How about m equals to 2? So this is the second one, second minimum. So this, like, I'm looking for m equals to 2, okay? So what we would do is, now we will look at this point and this, divide this into 4 pieces. So now we look at, I'm going to look at some new. So this point and this point, they, this and they come together, they kill each other. Next point kills next point, next point. So the this wave, this part of the wave kills this part of the wave, and this part of the wave kills this part of the wave. The earlier one, the top part of the wave, killed the bottom part of the wave. Now I'm going to have 4 pieces, and the 4 pieces, this part of the wave will kill this part of the wave by doing point by point matching. And so these two out of phase, that gives me d over 4 now sine theta 2 is lambda over 2. So the difference between these guys will be, this difference will be d over 4 sine theta 2. And so you can see this just turns out to be d sine theta 2 equals to 2 lambda. And you got this. You can actually play the next one. You'll have to split into 8 pieces and so on and so forth. Okay. So the further you go out, you have to split this wave into further pieces. And because this is a continuous wave, you can split in as many pieces as necessary. And of course, at some point, you're going to violate the law, violate the rule that this is can't be more than 1. And that's when you stop. Okay. So this is a nice trick to get what the minimum will be. This trick does not really work that well to give you the intensity of the, like different peaks, and to get a full analysis, you need to do a heavy-duty mathematical work. And at some point we'll do that, but right now I think this is justifies, this is not a derivation as such, but justifies why this formula will work. To recap, make sure that you understand that this m is not open-ended for whatever values you can get from the, a plug-in this formula will make sense. This formula makes sense as long as m does not violate the condition that leads to sine theta m greater than, has to be less than 1. And this only gives me minima. And for the maxima, we just locate by saying this is symmetrically placed, which not completely true. So if I had a minimum here and a minimum here, and then minimum here, to get this angle and this angle, you really have to do both of this angle and then get the middle, and both these angles get the middle. Okay. All right, I'll stop here and talk to you later. Bye.